So we have some topics here that are technically part of the embedded portion of our class, which is work without a calculator. How do we get our multiplication and division done with multi-digit numbers? Boy, long division is something that lots of people hate for lots of different reasons, and one of the reasons is so many teachers do a bad job of teaching it. So I'm going to give you a look at how I do long division, and we're going to visit it again later, a little more involved maybe with decimals and stuff. But I'm going to start from the beginning with long division. I'm not going to rely on you remembering a little of this and a little of that and having people all over the place. And by the way, you don't have to send me an email or anything about hating long division. I'm going to assume that almost everyone does. I know some of you don't. You don't have to send me an email about that either. But long division is something that can be done much more successfully than most people do it. And we need to understand what's going on when we do long division. So that's the second part of what we're doing here today. Right now we're going to deal with, here is multiplication. Multiplication does require you to learn about 55 math facts like 6 times 7. Okay? I would go around the class not calling on people to embarrass them, but just saying, you know, there are certain things that give people trouble. 6s, 7s, and 8s seem to give people the most trouble, right? You got things like this: 6 times 7, 7 times 8, 8 times 6. And people know there are certain numbers floating around that make those ones kind of confusing and all that, but 6 times 7 is 42, 7 times 8 is 56, and 8 times 6 is 48. If you knew them that quickly, you already have this part conquered. If you don't, we need to work on that. We need to make you better at it, but I'm not going to be chasing you around all semester with it. You're going to need to work on something that we have available to us. I'll show you that in a little while of where you can practice your times tables, but you got to get used to them. We're not going to have you buying flashcards. I'm not going to make you feel bad. Also, I'm going to tell you, you only need to know from 1 times 9 up to 9 times 9. 1 times 1 up to 9 times 9, I should say. Right? That would already be 81 of them, and then a lot of them are doubled, so it's about 55 different things. The toughest ones are these right here. Okay? What happens is, if we got 6, 7, and 8 as one of the factors of what we're multiplying by, and the other one is 6, 7, and 8, if you know one of them, you can probably get the rest. Okay, do you know 6 times 6 is 36? Okay, give me 6 more, that's 42. Give me 6 more than 42, that's 48. And most of the battle is won already. Because now, do we know 7 times 7? Those are perfect squares. 6 times 6, 7 times 7, 8 times 8. Those are ones we really particularly should know. But 7 times 7 needs to be known to be 49. And 8 times 8 is 64. But even if you didn't, having the 36 locked down could be pretty helpful to help you get the rest of them. Because what happens is this 49 is 7 times 7. If I had one fewer of the 7, that's a little tough because you'd have to do subtraction. But how about this? This is 6 times 6. That's with 6 of the 6s. Now I want 7 of the 6s, so give me 6 more. Here's 42. Now there's 42, 6. So now we're doing our 7s. 42, 7 more is 49, 7 more is 56. Now if we go 36 plus 6 is 42, 42 plus 6 is 48. That's right for there. Now we go 48 is 6 8s. Give me another 8. That's 56 when you add on and add another and you get that. And there are the 9 hardest ones. Wait a minute, who called them 9? I won't. These are the same. So now there's only 8. 6 times 7, 7 times 6. Each of those is 42. 8 times 7, 7 times 8. Those are the same. Each of those is 56. Now to get to 6 times 8 and 8 times 6, you kind of got to go off screen or go like up and around or something like that. But there aren't 9, there are 6 of them that are tough. Half of them are perfect squares. 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64. Those are some of the toughest ones. The other ones that people do mess up, 6 times 7 is 42, 6 times 8 is 48, 7 times 8 is 56. That's the 6 of them that are the toughest. You know, do people know 2, 4, 6, 8, all that to get through their 2s, 5, 10, 15, 20 to get through those? Yeah. 3s give people some trouble, maybe the 4s do. But the 9s have a cool thing going on with them as well. When we're going for the 9s, what happens is if you take 9 times 7, same as 7 times 9, what we have is 70 would be too big. So don't start with 70, start with 60. Now finish the 9. 6 plus what gets me 9? 63. 9 times 8 9 times 8 is not the same as 10 times 8. So 80 is too big. Go in the 70s. Finish the 9. 7 plus 2 makes it. That's how you get your 9s. There are other ways to get 9s, stuff like that. But we need to know our times tables. So I'm going to have you look at Zetamac, ZETAMAC.com. Then we'll leave that up and we'll take a brief video to take a look at it separate from this a little bit later. But this is for your times tables, your addition facts, your subtraction facts, the stuff that you can do instead of flashcards. I promise you there are no rainbows, there are no unicorns, okay, and no lollipops. This is really just let's get through it, time me. They give you 15 seconds, 30 seconds to try and do as many as you can, as fast as you can. And you can use it on your phone when you're waiting in line somewhere, or when you have just 30 seconds of downtime. So don't do Candy Crush or whatever it is now that people are doing, but do that instead. And you might improve your speed, especially if you focus it on the ones you need. Okay, so we do need times tables to be known. If you don't know the times tables, I'm not here to get mad at you. I'm here to let you know that that's a deficiency that you should be working on throughout the semester, but the class is not going to focus on that. Your job is to be good at that by the time you take your exam 1, and certainly by the time you take the final. Okay, we had two problems up here that I wanted to take a look at. 324, and I want to multiply that by 45. If I have a single digit number as the result of my multiplying, I can put that number right into play. But if not, I have to break it up into the last digit that I just found and the digit that's moving up to the next level up in our place value, such as this are units, tens, hundreds, units and tens. Here's what we have. 5 times 4 makes 20. Here's my 20. There's the 0 from 20, but over here I have a plus 2 because that's the 2 from 20 and that's the 0 from 20. This is ready to go to work. Now I'm taking my 5 and multiplying it by 2. That makes a 10. So that 10 goes over here where the 2 I just parked there a little while ago is waiting. And that 10 isn't really 10 because it's not 5 times 2, it's 5 times 20, which would make 100. But look, that 0 is there, so the 10 would drop there and it would be the 100, so it takes care of itself with place value. Now, 10 plus 2 is going to get me 12. This is my new number to work with. I park the 2 there from my 12, but I move the 1 from the 12 I just made here because I can't fit 12 into a single column. I can drop the 2 in there, the last digit can get its spot where it belongs, and now this has to move over here and be ready for the next column. When I go 5 times 3, I'm going to get 15. It's going to pick up the old 1. It just looks like a 1 to make 16. It's actually 100 and 1500, but it knows that by place value. So this 16 that I make, no other numbers to conquer, is going to go right here. And if I just had 5 times 324, I would be done. But I also have this 40. Now the 40 is going to function like a 4, but look, that 4 is 40, so I use a 0 right here. So the very first thing I make, instead of being in the units position, is going to drop there and automatically find its way into the tens position. Now I do need to know 4 times 4 is 16. I will put my 6 there, but here's my 10 from 16. Now I take my 4 times 2, which makes an 8. 8 plus 1 is 9. 9 will fit in a single column. So I'm going to put my 9 right there, and I don't have anything to do here because my 9 is fully there. If I wanted 4 times 24, I would get 96. 40 times 24 gets me the 960 you're looking at, and I don't know anybody anything right now, but I do have to go 4 times 3 and get a 12. There are no more numbers to conquer, so I put my 12 right there. And now my columns are ready. I have 0 plus 0, so that's an easy 0. 2 and 6 makes 8. 6 and 9. 6 and 9. If I take 1 off the 6 to make it a 5, throw it on the 9 to make it a 10, I'm going to see I have 15. The 5 will go there, but I need to push 1 up there. There's hardly ever a lot of room for that 1 to go. It doesn't make 11, but you usually make a little tiny 1 there, plus this large 1 that was there from the 1620. 1 and 1 is 2, and that 2 from the 12960. 1 plus 1 is 2, plus 2 is 4, no carrying over, and then 1 is the only thing I have there. What I would do then is say I have 3 digits of units, which is units, tens, hundreds. Then I put my comma, and then there's my thousands and my 10,000s. This value is 14,580 place value. Begins with units, then tens, then hundreds. Then we do the same thing followed by the word thousand. This is the thousands, nothing else to say. This is my 10,000s, and out here would be 100,000s. Then it starts over again with my millions, and then so forth. And we'll look at place values sometime in the near future. Okay, but you need to know, it's good to know up to trillion, because that's where we are now when we're talking about the cost of packages in the government that have to solve some major problems going on, such as in spring and summer of 2020. It goes like this: units, thousands, millions. After millions is billions. Now millions is like monopoly, one. Occurrence beyond thousand. Billions is like bicycle or binary. It's two notches beyond thousands. Trinomials would be tricycle, three steps beyond thousands. It goes like this: units, thousands, millions, billions, trillions. Okay, we don't have bazillions, and zillions does not exist, but we are at trillions now, such as the program in the spring of 2020 was $1.5 trillion bailout, and then there were more possibly coming. So that's in trillions. There is no bazillions, gazillions, zillions, none of those exist. Okay, after trillions we'll have quadrillions, quintillions, and let's hope we never owe that much money. But anyway, that's what's going on with place value. I got this other one, pretty much the same thing, looks a little bit larger, maybe not. 764 times 84. 764 times 84. All right, here we go. 4 times 4, you need to know it's 16. Float the 1. I'll just say float the 1, which takes the 10 from 16, puts it there for the next digit to come along. 4 times 6 is 24. Pick up the 1 for 25. Put the 5 in place. Float the 2 for 20. 4 times 7 is 28. Pick up the 2 to make 30. No more digits to conquer. 30 goes down. 3,000, no hundreds, 56. Now we come in and we deal with the 80. What's going to happen here is I'll put a 0. I don't need a special color. I certainly could do it to represent that I'm going to start using it as an 80, not as an 8. That's what the 0 puts it in the proper place. 8 times 4, you need to know, is 32. The 2 goes into place, but the 3 is going to float to the next digit. 8 times 6 is 48. Pick up the 3 for 51. Park the 1, float the 5 for the next digit. 8 times 7 is 56. 56 picks up the 5 to create 61. I can definitely put the 1 down there, and there's no more digits to conquer, so I can actually put the entire 61 there. 6 and 0 is 6, 5 and 2 is 7, 0 and 1 is 1, 3 and 1 is 4, and the 6 is untouched. This is 64,176. So, let's see now. Why did I have a different number on that? 64,512. I got 64,512 last time. So 3056, and then double that to, so seems right, maybe I copied a different problem down. 768 times 84. Okay, yes. We're good with the numbers that we have up there. I had a different problem written on my paper, so of course I had a different answer, but the work done there is very good, so we can work with that. I want to now show you how to do this with decimals. Decimals tend to make integers smaller. They don't change the digits that we have there. They change where the decimal point goes. So what I want to do is take a look at something like this. I would do all my digit work. If these were my digits, a 3, 2, and a 4 in a row, and then a 45 in a row, this is the outcome that would come from my work. But if I had 32.4 and 0.45, what that is not as big as 324. That's one move of the decimal to make it smaller, and 2 moves of that to make it smaller. So that's 1 decimal with that 4, second decimal digit is that 4, and the third decimal digit. All together, what happens is there were 3 times that I made this smaller. And what we do, if that was what my number was, all the digits will remain the same. But now, what'll happen is if I go 1, 2, 3 decimal digits, I'll go 1, 2, 3 decimal digits, and I will put my decimal point right there. Because each time that I have a decimal with a digit behind it, it means that I used a 10 for dividing to make this number appear to be smaller. The digits stay the same, but it's order of magnitude. We have base 10, count your fingers. If you didn't lose one or have some abnormality at birth, you'll have 10 of them. That's why we have base 10. And so every time we get to 10, we don't have another digit to write, another character to write in that digit. We move over and start using a bigger place valued location. Each time that we do that is division by 10. So this has 1, 2, 3 divisions by 10. Dividing by 10 moves the decimal to make the number look smaller. So what I want to do is I want to put 76.4 times 8.4 together as a problem for us. The digits will be 64176 in that order, but where does the decimal go? So you can think about it and try it. You can stop the video and try and do it yourself, but I'll tell you where it goes. We have 1, 2, total of 2 decimal digits. We owe twice to make this number look smaller. So it won't be behind this for this 6 over here. It'll be 1, 2 moves, and we'll get 641.76. And here's a way to check just for orders of magnitude, okay? What we have is 32.4 multiplied by less than 1. This answer should show up less than 32.4. Because we multiplied it by a number that's less than 1, we cut it down. This one we had 76. We multiplied it by 8. We're going to come back higher than 76. So we're not going to have a number lower than 76. We're going to come back higher than 76, and it turns out that we get 641, bigger than 76. We didn't make it all the way up to 764. We would have had to have at least 10 to get us to 764. So that's how we do our multiplying with decimals. You do the work the same as though there was no decimal, and then you account for how many decimal places are there total to cause your digits to shrink their magnitude, their order of magnitude, as we see how many tens did it divide by. So that's how we handle all of our multiplication. Multiplication, if you start with no decimals, you'll end with no decimals. If you start with a decimal, many times you will end up with a decimal. You can divide 2 integers and come up with a decimal or a remainder when you do division, because division is repeated subtraction. It's the same thing being subtracted over and over again. And I want to set up division for you here and take you through the process of how to do it. So the first one I want to do in long division here is 8,330, and I want to divide it by 17. Okay, how does that look? Not great for what we have to do right now. I want to take my 8,330, put that under the fraction bar, and in front of it I want to put 17. And here's how I do it. Long division should be done in pencil, not pen. If you know anyone who does crossword puzzles in pen, is that a reason that you like them? It's kind of annoying. But that's what people do, like, oh, I'm so brilliant, I can't make mistakes. They do make mistakes, and it's not a mistake. A crossword puzzle is a series of guesses, and you need an eraser so that if your guess is incorrect and proven by later work, then you come back and you fix that guess to a guess that's better until you got the guess that's perfect. So when your first guess isn't right, that's no problem. That's science. Science is not about making a guess about what's going to happen and getting it right. And you're a brilliant scientist if you did that. No. Science is about making a guess that can be tested. And when we find it's not correct, how can we make it better? That's what's going on with long division. So you don't do it with pen, you do it with an eraser. You shouldn't feel stupid if your guess isn't correct, and I'm not going to try and say, what's the matter with you? How come you don't see that's a 5? I'm guessing some of us have had that experience in the past, and that's why so many people hate long division. I want to give you not just me saying, take a guess, guess anything. I want to give you some guidelines toward making a good guess, but it might not be perfect, and how to fix it when it's not perfect. So erasers are not like they have in the dollar store, the big things, errors for people who make big mistakes, eraser for people who make big mistakes. No, erasers are sometimes there for science too. Here we go. If I had to do, 8 divided by 2, which the answer is 4, it would look like this, 8 divided by 2. How many 2's are in 8? There are 4 of them. I put it in the exact same spot where the 8 is. I would put my 4. I would do 4 times 2 and get the 8 and subtract, and then I'd have nothing left over, which means it's a perfect fit. It has 0 remainder. It doesn't have any extras hanging around. Okay, if we have something like this, 32 divided by 8, If you know that 8 times 4 is 32, then you'd say, all right, I need a 4. You don't put it over the 3 because 3 doesn't have any 8s in it. You need the whole 32. So you put your 4 over the 2 because you're using all of 32 to do 4 times 8, and then you write your 32, and that works out. So you're not always going to drop the digit right over the first digit that you're looking at. You're going to drop the digit at the end of the number you used at that instant. So here we go. I have 17 divided by 83. Do you know how many 17s are in 83 exactly? Neither do I. So what we're going to do is we're going to go with 83 divided by 17. I guess 17 is closer to 20, so I might think of it like a 20 there and say this is a 2 because 17 goes up to 20 and 83 is like 80. And so now how many 20s are in 80? Well, that's exactly 4. But I needed 80. I couldn't do 8s. 8 doesn't have any 17s in it. 83 has some 17s in it, so I'm going to try 4. Now, if you tried to do 8 divided by 10, it would still work eventually, but then you would have an 8 up here. And whichever number you have up there, you go like this: 4 times 7, and that's 28. So I float the 2 from my 20, just like in multiplication, because I am multiplying here. 4 times 1 is 4, and that gets me 6. Okay, so let's see what happens here. I got my 4, and the 6 that it created, no more digits to conquer, so I put my 6 there, and now I have to do my subtraction. Now, if you could do 13 minus 8 and get the number, that's awesome. But if not, that's fine. I have a method for you. This 80 has more than it needs, and we got to make this up to a 13. So I'm going to take my 80 down to 70 and 10. That's the 70. The 10 goes right there to make 13. 13 minus 8, do you know it's 5? That would be great. If you don't, that's okay. Because you give this 2 more, and that becomes a 0. Give this 2 more, that becomes a 5. And you did what the 13 minus 8 does. Now you got 7 minus 6 is 15. Awesome. 15 is positive. 15 is smaller than 17, so I get to keep going. If I got my number here that wasn't 4, if I got a negative number trying to show up here, I got to go back and take away less than 4 of them. If I got more than 17 left over, I got to go back and take away more than 4 of them. That's what the eraser is for, and you're not an idiot if you got a different number to start with. But as you narrow it down, the only number that'll work is 4. If you used a 5, it'll make 85, try to go negative. If you used a 3, it'll come up with 51, and it'll leave you with 32. And neither of those is right, but the 4 is what lands in between. So now, 15 can't divide by 17, that's perfect. Now we move on to try and get our next digit. 153 divided by 17. Remember, I treat this like a 20, so I don't look at 153 divided by 20. I look at that 15 and I divide by the 2 that's there. Right? This is 20 that I'm thinking of. So I don't look at the whole 153. I only look at the first 2 digits giving me 15. And I look at this making the 2. So 15 divided by 2, 8 is too big. I'm going to try 7. Let's see. 7 times 7 is 49. Float the 4. 7 times 1 is 7. So I get 11. And I come in here and I got 11, and I try and do my subtraction. 3 minus 9 is not going to happen, so I turn this into 40 and 10, make it 13. 1 more there gets me a 4. 4 minus 1 gets me 3, 34. I'm not stupid. I did what I thought I should do with my guess. I don't feel like, oh man, it's terrible, this crumble it up, I hate division. No, 34 is too big. So let's see. If 34 is too big, I need to take more away. Let me go, and this is not because I'm stupid, it's because we're trying stuff out. That is 153, and I need to take away more. Do you know how much more I should take away? If I'm not sure, I'll probably just, since it's a 7, I'll go up to 8. If you're thinking 9, maybe that's better. And if you did that, you get there quicker. But if you think 9 and that's too far, you're going to have to come back and erase again and hit the 8. Okay? We're going to try 8. 8 times 7 is 56. That's one of the tough ones to know. So we go with the 5 for 50. 8 times 1 is going to get me 8. Add the 5, it's 13. So now 150 can go down, the 50 can go down to 40, and 10 can make 13 again. 4 more here, 4 more there, that gives me a 7. Okay, 4 minus 3 gives me 17. Oh, there's an extra 17 in there. I should have gone with 9. I mean, I have to eventually get to 9, and if I went all the way up to 9 instead of 8, I'd have had it already. So this is 153, and I'm going to go with 9. And I know what I'm doing. You may not believe that, but it's true. So now I'm going to go 9. 9 times 7. Okay, 9 times 7 is 63. Float to 6. 9 times 1 is 9. 9 plus 6 is 15. No more numbers to conquer. Boom. 0. All right, the answer is not 49. Look at this thing. I'm not done. What I have to do is bring the 0 down. 0 has rights, so does 1 in my classroom. You may not always see them the way that they work, but 0 works, 1 works to do its job. Here is 0. How many 17s are in 0? None. Put your 0 there. Now you've taken to the end, and this number is 490. And there's no remainder, 0 remainder. If there is a remainder, there are 2 ways to deal with it. Not to put an R followed by the remainder like the first time people teach you that, but to either continue beyond the decimal point with zeros, so it terminates or repeats, or to take your remainder and put it over your divisor, the thing you're dividing by. So here I have 490 plus I have 0 over 17. Because it's 0, I don't write it, and 490 is what I get. That's how we do long division. I want to get you used to long division, so shorter division can be handled by having fewer steps.